Lesson 11-8 Polygons, and in this lesson you learn to classify polygons and to determine the sum of the measures of the interior and exterior angles of a polygon. So let's take a look at the concept. The figures that you drew above will definitely didn't draw anything. So this is referring to the modeling with technology activity, which we didn't do. Okay. Let's move on to the definition of what a polygon is. So a simple closed figure can be traced by a continuous path without tracing any other point other than the starting point more than once. So a polygon is a simple closed figure in the same plane that is formed by three or more line segments. Okay, so definition of a polygon: a simple closed figure in a plane that is formed by three or more line segments. Okay, and we call those line segments sides. So the segments meet only at their endpoints. These points of the intersection are called vertices, plural of a vertex. Okay, so a polygon will have sides, at least three sides, and they only meet at their endpoints called vertices or a vertex. Okay, and some examples of plane figures, which are polygons, are these. Okay, so if you notice, they have sides, and if you notice, they meet at endpoints called vertices. So that's a vertex. Every point that I draw will be a vertex. Okay, so those are all vertices of the polygon. Okay, so some examples of non-polygons. Okay, here are some examples. Why? This particular case, because this curved line is not a side, okay, because it is not straight, okay, and this one, for example, it is not a simple closed figure. It is a series of closed figures interconnected to one another. So these examples are not polygons. These two are examples of polygons. Okay, and in a polygon we can classify polygon by the number of sides. Some of the more common polygons are shown below. Okay, hold on, before we do that, I forgot to do this. Think about it. Can you name a simple closed figure that is not a polygon? So we have a simple closed figure that is not a polygon, and the most probably common figure that you can think of is a circle. A circle is a simple closed figure, but it's not a polygon. Why? Because it does not have line segments, which we call sides. Okay, so let's go back here. Classification of polygons by the number of sides. A triangle is three sides. We know this is the shape of a triangle. Quadrilateral, 4 sides. Pentagon, 5 sides. Hexagon, 6 sides. Octagon, 8 sides. Decagon, 10 sides. Okay, so if you're looking at the words right here, octagon, octopus, 8 sides. Okay, and decagon, when you talk about the decade of the rosary, that's 10 as well. So the prefix of the word more or less tells you that how many sides a particular polygon is. Okay, for example, a quadrilateral, quad means 4, penta means 5, tri means 3, hexa means 6. Okay, now you might ask, why is it October? Well, it's not far-fetched, because in the olden times, October used to be the 8th month of the year. And because of Julius Caesar and Augustus Caesar, we added July and we added August. And that's why October was pushed to the 10th month. And if you notice, December, DEC also, okay, used to be the 10th month of the year. Okay, and November, okay, used to be the 9th month. Okay, so a polygon with sides, with an end sides, is called an engon. Okay, so if you don't know the number of sides of a polygon and it's designated with n, it's called an engon. Okay, so a diagonal is a line segment that joins two non-consecutive vertices. You can draw diagonals in any polygon. So the definition that you need to write down right here is a line segment that joins two non-consecutive vertices. Okay, so you can draw diagonals in any polygon with more than 3 sides. So if it has more than 3 sides, Okay, you can have a diagonal. Remember, more than 3 sides. Therefore, a triangle does not have a diagonal. Okay, so in the polygon shown below, all possible diagonals from one vertex are shown. Okay, the table shows the number of diagonals drawn and number of triangles formed by each polygon. So let's take a look at the first one, which is a quadrilateral. Remember, a triangle does not have a diagonal. So in a quadrilateral, you have 4 sides, one diagonal, which is that line right there, and then you have 2 triangles. Okay, in a pentagon, such as this one, you have 5 sides, 2 diagonals. The 2 dashed lines indicate your diagonals, and you have 3 triangles, 1, 2, 3. In a hexagon, okay, you have 6 sides, and you have 3 diagonals from one vertex, and you have 4 triangles form 1, 2, 3, 4. Heptagon, you have 7 sides, okay, which is this one, okay, and it has 4 diagonals from one vertex, and 5 triangles have been formed by those diagonals. And finally, an octagon is 8 sides, 5 diagonals, and 6 triangles form 1, 2, 3, 4, 5, and 6. Okay? So, compare the number of sides to the number of triangles. What pattern do you see? The number of triangles is always, okay, 2 less than the number of sides. So if you look at this one right here, okay, the number of triangles will always be 2 less than the number of sides. So 3 triangles for a pentagon, but it has 5 sides. 4 triangles for a hexagon, but it has 6 sides. 5 triangles for a heptagon, but it has 7 sides. And 6 triangles for an octagon, but it has 8 sides. So it will always have 2 less than the number of sides. You can use diagonals in the property of the sum of angles of a triangle to find the measures of the angles of any polygon without using a protractor. And this is what we come up with. Okay, sum of the interior angle measures in a polygon is this. So if a polygon has n sides, then n minus 2 triangles are formed, and the sum of the degree measures of their interior angles of a polygon is n minus 2 times 180. So when you talk about interior angles, it means the angles inside your polygon. Okay, that's how you find the sum, okay, of the degree measures of the interior angles. Will be this formula, the quantity n minus 2 times 180. And let's see how we use this in example number 1. Find the sum of the measures of the interior angles of a pentagon by drawing diagonals. Okay, first we draw our pentagon, okay, which is right here. There's your pentagon. So draw all of the diagonals from one vertex of our pentagon. So let's say we'll use this vertex, and let's draw one diagonal of our pentagon, which is that one, another diagonal, which will be that one. Okay, so after we draw our diagonals, we form 3 triangles, 1, 2, and 3. And we know that the sum of the measures of the interior angles of a triangle is 180. We know for a fact that each triangle formed by our pentagon will be 180 degrees, the sum of the angles, that is. So that's 180 degrees. 180 degrees. Okay, so we simply multiply 3 times 180, or 540 degrees. Okay, now the way to do this is to use the formula that we talked about. So that will be n minus 2 times 180, and this is simply, n represents the number of sides, so this is basically 5 minus 2 times 180, or 3 times 180, which is the same thing as 540. Okay, so let's take a look at letter B. Find the sum of the measures of interior angles of a hexagon by using the formula. Okay, so we want to find the interior angles of a hexagon, and we know for a fact that a hexagon has 6 sides, therefore n will be equal to 6. So we use the formula n minus 2 times 180, okay, which is equal to 6 minus 2 in quantity, multiplied by 180, and that is the same as 4 times 180, or 720. Okay? And therefore, the sum of the measures of the interior angles of a hexagon is 720. Okay, we keep on referring to the word interior angles because we're simply looking at the angles inside our polygon. That's why they're called interior. Okay. Next concept we need to learn in this lesson is what we call a regular polygon. So a polygon that is equilateral, which means all sides are congruent, and equiangular, which means all angles are congruent, are called regular polygons. Okay, so when you have a regular polygon, all sides are congruent and all angles are congruent. They are both equilateral and equiangular. Okay, since the angles of a regular polygon are congruent, their measures are equal. Okay, so the Pentagon in Washington, D.C. is named for its unusual shape, obviously, because it looks like a pentagon, 5 sides right there. Okay, what is the measure of each angle of our pentagon? So we know for a fact that the scale model and the actual buildings are similar figures. Okay, so in similar figures, the angles are congruent. From example 1a, you know that the sum of the measures of the interior angles of a pentagon is 540. Since the pentagon is regular, which means it's equiangular and equilateral, you can find the degree measure of one angle by simply getting 540 and dividing it by 5. Okay, once you do that, divide that by 5, you end up with 108. The measure of each angle in a regular pentagon is 108 degrees. Okay, and we're talking about interior angles still. Okay, in the next slide, we're going to talk about exterior angles, and let's see. So the angles were considered in example 1 and 2 are inside the polygon. These are called interior angles. When the side of a polygon is extended, a special angle is formed called an exterior angle. So in the activity at the beginning of the lesson, you discovered the interior and exterior angles of a polygon are supplementary. So when you talk about interior and exterior angles, okay, they are supplementary. Okay, right here. So the interior and exterior angles of a polygon are supplementary. Okay, you also discovered that the sum of the exterior angles of a polygon is 360. So when you talk about two things that you need to remember, two things that you need to write down. Okay, first thing is, let me change the color to red right here. The interior and exterior angles of a polygon are supplementary. That's the first thing. And the second thing is the sum of the exterior, all the exterior angles of a polygon is 360. You need to write this down in your notebook because this becomes very important. Okay, so you can use these ideas for another way to find the measure of one angle of a regular polygon. So in example number 3, you're being asked to find the measure of each interior angle in a regular hexagon. Okay, so they're being asked to find each interior angle in a regular hexagon. Okay, and before we start with example number 3, the secret word for this particular lesson would be outside. The secret word would be outside. Okay, so we want to find the measure of each interior angle in a regular hexagon such as this one. So let's take a look at how we can do that by looking at exterior angles. So first we sketch it. That's your regular hexagon. And then the second thing we need to do is draw an exterior angle at each vertex. And the only way to do that is when you simply extend. Okay, if this is your regular hexagon right here, you simply extend that line, okay, out like that. And that now you have your exterior angle. So draw an exterior angle at each vertex. You simply extend that line to be able to draw an exterior angle, and so on and so forth. Okay, so after you've drawn your exterior angle, okay, the next step would be counting the number of exterior angles, 1, 2, 3, 4, 5, and 6. So there are 6 exterior angles, and we know for a fact from this particular sentence that the sum of all the exterior angles of any polygon will be 360. So their sum would be 360. So we know for a fact if we add angle 1, angle 2, angle 3, angle 4, and angle 5, and angle 6, it will be equal to 360. As since it's a regular hexagon, all we need to do is divide 360 by 6. So the measure of each exterior angle would come up to be 60. But we want to find the interior angle. So what we can do now is look at this sentence. The interior and exterior angles are supplementary to each other. So it simply means that we get 180 and subtract 60 and you get 120. So interior and exterior angles are supplementary. The measure of each interior angle in a regular hexagon is 120 degrees. Okay? And that's the end of our lesson. Thanks for watching.